that's going to be an isometry. So these are the lattices of class number 1. Turns out that there's only finitely many of those in total. And they only occur in rank up to and including 10. They do occur in rank 10, but never beyond rank 10. The Nice Theorem by Watson. This is G.L. Watson, not to be confused with the other Watsons in number theory. I think there's one, G.N. Watson. This is G.L. Watson. Proved this in 1963. And it turns out, I just mentioned this in past, it turns out that our friend IN here has class number 1 up to and including n equal to 8, and then never again. That class number increases very quickly after that, which is the explanation for that result that I had. U of k was k plus 3 up to k equal to 5, because up to that point you're hitting the sum of k plus 3 squares has class number 1. Check that those things are locally represented, therefore they're globally represented because it's class number 1. And that's what breaks down then when you get to 6, because I9 does not have class number 1. I think it just has class number 2. So again, we have a finiteness, nice finiteness theorem, so the next logical question is, can we find them all? And the answer is, well, Watson tackled this problem. Apparently, as far as I know, he did all of the calculations by hand, and found all of them. There's a whole series of papers. I think 1963, I believe, was the first one. They run through 1985. He got all of them for n greater than or equal to 6, and many of the ones in for n equal to 3, 4, and 5, but he wasn't quite able to finish those off. But there's a recent result of Kirschner and Lorch that finished off these small dimensions. There's lots and lots of these things in small dimensions, very few as you get to higher dimensions, as it turns out. There's only 2 of them when n is equal to 10. There's a couple hundred of them in these earlier ranks. So Kirschner and Lorch were able to develop some computer algorithms to enable them to finish off this problem. Incidentally, all these finiteness results, these enumeration results, if you want to see them, you can find all those. I don't think I mentioned it. The universal ones, there's 6,436 of them. You can find them if you want to see them. There's the Google catalog of lattices. There's a massive online database of these things that was maintained for many, many years by Neil Sloan at Bell Labs, and has now migrated. It's maintained by Gabriele Neve at Aachen in Germany. Everything that's known about enumerating lattices with any kinds of properties appear in that database. You can find all of these guys, including this list of this final list of Kirschner and Lorch. Okay, so that tells us what happens at the left-hand end of that string of containments. It turns out that the next one, I get nothing new at the next step. If I look at Rn n minus 1, there's a nice theorem of Kitioka's that dates from 1978 that basically says positive definite Z lattices are determined up to isometry by some local data and the lattices of codimension 1 that they represent. So as soon as you have class number bigger than 1, then you have, he proves that you have something of codimension 1 represented by 1, but not the other one. So there are no new ones that come up here. So that turns out you get nothing new at that stage. And this, the generalization of this to totally real number fields was in Nick Meyer's dissertation a little over a year ago. Kitty did only the case of Z. Okay, so let's look at the other end for a few minutes. What can I say about the other end if I look at Rn1? Turns out that R31 is finite. This is a very nice, this was in Watson's thesis in 1953 that was never published. Another unpublished thesis that laid around for many years. And he actually enumerated many of these. Now we said earlier UN1 is infinite, so therefore Rn1 is infinite for all n greater than or equal to 5. Okay, so it leaves the question, what about n equal to 4? What about R41? Well, the first, it turns out that it's infinite, and the first infinite family was in a paper of mine in 1995. There's lots more known now, but I think that was the first one in an event. And there's now actually a complete list of these guys in the ternary case. Burton Jones found the diagonal ones back in his thesis. He was a student of Dickson's at the University of Chicago in 1928. He found the 102 diagonal regular ternaries, positive definite ones. And Kaplansky became interested in that problem in the mid-90s to just try to actually complete this enumeration that was started by Watson. And he recruited a couple of colleagues. Will Jaggi was a colleague of Kaplansky's at Berkeley, and Alexander Schiemann is in Germany. He recruited them to do some of the computational work, given the computational power that was available by that time. It should have been possible to complete the determination, and in fact it was. There's a nice list, actually that's what the paper is, a list of 913 lattices, the regular ternaries. Actually, well, they're not all quite known to be regular, as it turns out. 22 were originally identified only as candidates. They could rule out all the others, so most of these 913. 22 remained as candidates. O was able to prove that 8 of those guys were regular in 2011. And now we have at least a conditional proof under a generalized Riemann hypothesis since 2014 by Robert Lemke Oliver. So there's still 14 holdouts that haven't been proven, at least unconditionally, to be regular, but the list is essentially complete. Okay, so what can we say if for k regular lattices of k when k is greater than or equal to 2? Not a whole lot, but here's what we can say. The first result of that kind was mine in 1994. I can prove that R42 is finite. There's only finitely many quaternary lattices that are 2 regular. By extending the techniques of Watson. Let's say we know that UN2 is infinite whenever n is at least 6, because U52 is non-empty. That's that old Mordell theorem. So Rn2 is infinite for all n greater than or equal to 6. So what happens to R52? Well, I wasted some time having gotten this one and having gotten R41 to be infinite. I assumed then when I went up to R52, it would be infinite, that I could construct some infinite family. But I failed, and the reason I failed is it's not true. as was proven a little bit later. I'm glad I didn't prove it in retrospect. Chung proved this in 2001. That actually R52 is still finite. And then the generalization, Chan and O have the nice generalization that R in n-3 is always finite for all n greater than or equal to 5. You can always get this codimension 3 finiteness. Very nice theory. It's probably not, it's certainly it's best possible in general, but probably not. It can probably be improved for larger n. It could surely be improved for larger n. But it's a nice. This is the nicest complete theorem that we've got. So what can be said about enumeration here? This is kind of interesting. The enumeration here is very partial and incomplete, but O looked at the even lattices in R42. Now by even, I just mean they only represent even integers. Okay? So it's not all of them, but a fair number of them. And he found 177 of them. And that's all of them. Proved that that's complete. It turned out, after he had the list, he checked the class numbers, and it turned out that all of them have class number 1. All the 177 in his list. So this is kind of suggestive, unless evenness has something very special to do with this. It could be that in fact every lattice in R42 has class number 1. I don't know. So there's one question. Are there any lattices in R42 that have class number bigger than 1? It would be interesting to know one way or the other. Or is it possible that R42 is equal to R44? That could be. We don't know. Is there any n greater or equal to 4 for which Rn n-2 is not the same as Rnn? We know that Rn n-1 is the same as Rnn. That's Kitty-Otis' theorem. Could we go one step further in that chain and still have equality? Don't know. Maybe. It's not known. So let me look just to kind of review things. Oh, these don't show up very well. This was going to be my political statement of the day. If you look at them on the computer, there's some that are colored blue and some that are colored red. So you have to use your imagination here. The blue ones are finite and the red ones are infinite. That was a random choice, by the way.
So the last two are red, right?
The last two are red. Yeah, your eyes are better than mine. The last two are red. So these guys. So we know this one is finite. R6 actually it turns out that there's 186 lattices there. Class number 1 of rank 6. I just looked it up in the catalog of lattices, and we'll forget that very quickly. But I remember it. I remembered it this long anyhow. Okay, so there's 186 here. We know these are always the same as these. We don't get any new ones when we go down to R65. Maybe, I don't know whether we get any new ones when we go down to R64 or not. Maybe we do, maybe we don't. Unknown. And then, if we go down to R63, this is this codimension 3 result. We know we still have finiteness to here. But now if we work in from the other end, these are infinite. This is our Rn1. We've talked about that a couple times. This guy is also infinite because, let's see, why is that? Because our friend I5 is in U5-2. So therefore U6-2 is infinite, therefore R6-2 is infinite. Okay. Now, this same thing happens up to n equal to 9. You won't see anything different. But at n equal to 10, it strikes me as kind of interesting. Because now you start at R1010. These are the class number 1. There's only 2 of them now. They've almost petered out completely. but there's still two of them there. And then your codimension 3 gets you finiteness down to R10.7. If you work up the other way, you can get infinite up to R10.5. Let's see, why is that? I guess that's because if I look at k equal to 5, the sum of 8 squares, that's that k plus 3 result, so I can get up to 8 squares, is in U8, 5, so therefore U9, 5 is infinite, and so therefore U10, 5 is infinite as well. But here, this one, you can't maybe tell it, he is neither red nor blue. He's undecided, I guess. So stay tuned. Is he finite or infinite? I don't know. This is the first place where they don't where they don't match up as you go. Okay. So let me just say real quick. One of the things that we looked at, Jiyoung Kim was visiting here a couple of years ago when Nick was still a graduate student. And we got interested in this same problem only not for k-regular lattices, but for what are called strictly k-regular lattices, where you have the same property but only for primitive representations rather than arbitrary representations. And it turns out that that's a stronger condition than just k-regularity. Not real obvious, but it's not hard. I think there's a proof of it in Nick's thesis. But in fact, when you look at the R41, we said R41 was infinite. R41 star, when you look at these strictly one regular ones, quaternaries, that cuts you back to a finite list. So that we can prove that you then have finiteness. We found the diagonal ones. There's 94 of them, with the largest class number being 7. And again, there's a generalization. In fact, in this case, the codimension 4 is the correct generalization of this. Alicia Marino talked about this back in May when she was here for the Langenhoff conference. Mentioned this result. I believe it's been submitted now, but this is still some work in progress. So there's many questions having to do with strict regularity, and I'll just leave you with a sort of a list of some other a few random examples there. But you can find lots of papers in the literature on various other types of regularity that I've mentioned here, either slightly different regularity conditions or applied to, for instance, Hermitian lattices. Maybe you don't have a bilinear form on your model. You've got a skew symmetric. I'm sorry. Maybe you don't have a symmetric one, but you have a skew symmetric bilinear form. You can look at regular lattices over polynomial rings over finite fields. Although don't look too hard, because I think that's already completely done. So these are all in various stages of development. So I think I will leave you with those and stop there. Thank you again.
Sets of lattices, are they just, is there any order among them, or just...
There doesn't seem to be any order. There doesn't seem to be very much structure there that you can get. You don't have much structure that you can get your hands on, unfortunately.
So not related.
You don't form your own lattice.
Well, the nice thing, and this was one of Watson's observations that got buried in his thesis for about 30 years. Or longer than that, actually. Kaplansky told me about this, and I found it quite amazing and didn't think it was true. But he said, "Okay, I'll send you a copy of the thing." So I looked. So of course he was right. what you can do, he found some transformations that allow you to transform if you have he was looking at just the regular ternaries. That if you found a regular tern, you had a way of descending by changing powers of prime, just by changing at one localization. Very nice. So that what you end up are sort of these chains of these things within that big set, that 913 set. You have these chains of lattices that descend there, and that does give you some element of structure. Yeah.
Maybe there is some connection between this study and some representation of the sum of cubic power of integers. So, for example, how many, or can you count all integers by sum of 2
cubes?
Yeah, or the 3 or 4.
There are some results. The problem, what makes this particularly intriguing from the perspective of quadratic forms is that if you look at the rational problem, there is a local global principle for rational representations by quadratic forms. So if you have everywhere representations over QP, you get an actual representation over Q. Already for cubic forms or other forms of higher genus, you don't have that kind of a local to global principle already, even rationally, that there are obstructions.
Oh, I see.
So the problem becomes much more complicated. I think they're very interesting problems, but they become much more complicated, and there's much more technical detail that you have to go into to try to come to grips with these local obstructions. Yeah. And I think that the local theory is not as complete either, although that may be just my naivete, but I think that's also not so complete.
Right.
No, so stay tuned. Maybe in 50 years or so. Yeah.
Any other questions?
Maybe like a very general question. Does the existence of certain types of those lattices imply existence or validity of some other algebraic structures? Like outside of just number theory. Is there any?
Not that I'm aware of. I mean, the question is, so when you're looking at these positive definite lattices, they embed in Rn. Okay, just take over Q. So they're lattices in Rn in the usual sense. So some interesting families of lattices have properties having to do with sphere packings and applications in cryptography or coding theory or geometry. But I'm not aware of any for these particular ones.
Okay, let's thank Andy.